Our next speaker is Dr. John McGaughey. John is the president of Miro Geoscience. He is a geophysicist with academic background and extensive industry experience in geological engineering with a focus on integrated interpretation for mineral exploration and geotechnical decision support. Prior to founding Miro Geoscience in 1999, he spent 10 years at Noranda Technology Center as a senior scientist in the rock mechanics group. Miro Geoscience is a software and consulting company specializing in integrated 3D interpretation and data management for the mineral exploration and geotechnical sectors with offices in Montreal, Vancouver, Brisbane, and Perth. John will share how 3D targeting led to discovery successes from regional to in-mine. Please welcome John McGaughey.
Thank you. Okay, thank you. The overview of the talk you see here. First, I'll give a little bit of context, and I want to talk a bit about managing the 3D targeting process. It's a lot more than technology. A lot of it has to do with how you think about putting things together and going through a targeting process. I'll talk a little bit about the 3D model creation, query, and target generation. And then I'll move on to some case studies as indicated from the regional scale through the prospect to the in-mine scale. So the modern exploration context, as you've heard several times today, undercover, at depth, brownfields, or system recognition rather than anomaly recognition. We have to deal with 3D multidisciplinary data. How do we get the geological, geophysical, geochemical data all together so we can make the best targeting decisions? And interpretation in model space rather than data space. So the picture there indicates some data. It's gravity data and a model underneath it, which is a geological contact. That contact is directly inverted from the gravity data under a number of constraints. You see some drill holes there. So the drill hole pierce points are part of the constraints, but there are many others not shown. But the idea here is that we want to get away from interpreting the map data and interpreting the geological structures directly as best modeled from that data. But this talk is about targeting more than it is about modeling. And what do we want to do when we target? Well, we need to recognize an OR system in complex multidisciplinary data. It really is a 3D data integration and interpretation challenge, as you heard about in many talks already today. For whatever we're targeting, we're going to start with a conceptual model, and this is a conceptual model shown here for VMS. And what we really want to focus on is what are those aspects of the conceptual model that we may be able to see in data and that we may be able to include in a model from which targets can be generated. The classic approach to quantitative targeting is from GIS. So this has been going on for about 30 years. A lot of the early work was done at the Geological Survey here in Ottawa. And the idea here is a simple one. If you can create maps of the different exploration criteria that are relevant to whatever it is you're targeting, perhaps you can combine those maps into some kind of quantitative mineral prospectivity map. So here we're showing gold potential. It's a weights of evidence model. But it really doesn't matter so much how we calculate the gold potential. What matters is that we're able to individually map the individual targeting criteria and then somehow combine them. So this kind of mapping has had some success. As I say, it's gone on for about 30 years. People do it now with neural networks as well as weights of evidence or logistic regression. There are many types of techniques for combining the data. But the success has certainly been mixed. It's not unmitigated success, and I think a lot of the problems with it are problems of scale, but even more so problems that we're working always here in data space rather than model space. We've heard a lot about the combination of geological and geophysical data today. If we're looking at geophysical data in this kind of framework, we're always looking at maps, gravity data or magnetic data or some other kind of geophysical data. And something that we certainly have learned is that we need to go from that map of data into a model. So can we do better in 3D? Well, this kind of technology can be applied now in 3D. We saw in Bruce's talk earlier a weights of evidence example where 3D data cubes were combined. If we're going to be able to do this, we need to be able to build these models for each of the individual criteria. So what are shown here in this suggestive picture are 6 different exploration criteria. Doesn't really matter what they are, but the point here, and I'll get to some case study examples later, the point here is that they can somehow be combined to reveal targets. So in the image on the right, you're seeing some targets. So those are those orange cubes, and they're somehow developed by combining the different individual criteria that are represented as properties in that 3D data cube. So the 3D data cube isn't the only way in which you could quantitatively integrate data, but it's a decent way, and it's a fairly simple way to think about. And if we're going to be able to apply the kinds of things that Alan King talked about earlier, artificial intelligence, we at least need some kind of data support that's in model space. And a 3D block model is not a bad place to start. So what I'll be talking about in terms of the modeling and then through the targeting case studies is really how to construct these 3D block models and then how to drive them forward to query them for targets. So probably the most important thing I've learned in the last 10 years or so that I've been looking at quantitatively combining different data sets for targeting is you have to have a plan. So we call that the targeting workflow. I'm sure there are many processes that could ultimately yield the same kind of benefit, but we have organized a kind of process for thinking about these projects. And if I could really summarize the biggest lesson of all, it's don't turn on the software too soon. You need a plan. And that plan's got to start with an objective, and the objective has to be as closely defined as possible. For example, if we're exploring up in the Abitibi and we're exploring for VMS, we're going to be creating a very different model than if we're exploring on the same ground for gold. So you really have to think about the objective closely before you start bringing data into software and constructing a model. So number one is the objective. From the objective, there will be a conceptual model. The conceptual model obviously is going to be different for different types of deposits and in different places. That conceptual model leads directly to the exploration criteria. So when you see pictures, whether they're cartoons or not like this of a conceptual model, there's a lot of characteristics you see there. Some of them are observable in exploration data, many of them are not. Which ones are, and how are you going to see them in exploration data, and how are you going to include them in a model? When we've undertaken these projects with clients, what we do is we go through a fairly systematic process of listing out what the exploration criteria are. And again, over the last decade or so, I've been in many meetings. There's sort of typically a half-day brainstorming session with people on site who have a lot of site knowledge and a lot of deposit knowledge about the exploration criteria and the conceptual model and how we're going to represent the criteria in the model we're going to build for targeting. Those are usually pretty interesting discussions. You might think that you could show up and meet a group of people who are fairly expert on the deposit type and the site and just write down the list, but not so. It's always a debate, and it's an interesting one, and it's a debate that you need to go through before you start the modeling process. And when we undertake these projects, we always build a table like the one you see here. I'm not sure if the writing is big enough to be legible, but on the left-hand column you see a list of exploration criteria. If it's not legible, I'll read a few of them: distance to exhalite horizon, distance in volcanic faults, rock type, sodium depletion, adulteration. These are VMS criteria. Typically, we're looking at a couple of dozen criteria that are modelable from exploration data that may have some impact on the vectoring process. So we list those. We understand what the metric is. We understand what the data required is in order to include it in the model. And we understand what the model representation is going to be. So this goes right from the base geological map and drill hole data through the geophysical data, the geochemical data, to an understanding of how each of those individual data streams are going to find a representation in the 3D model on a common support that can later be queried from which targets can be generated. It's only then we go through the data compilation and interpretation phase. The data compilation phase is usually the most difficult. It's getting your hands on the data, which is in various states on paper, digitally, various coordinate systems. It's all over the place. That process usually is a process of months following the sort of day or two of building a plan. And from that data, you always have to do some primary interpretation. Certainly, rock codes are usually not consistent across drill holes or between the drill holes and the map. That's a simple example, but there's a lot of other interpretation and normalization that has to be done. This shows just sort of the process of putting some basic data together for VMS up in the Abitibi in a 3D GIS framework. So we're looking at geochemistry data, we're looking at statistics of data, sorting out good data from bad, looking at cross plots, bringing in this case, a seismic section, looking at structure, looking at geochemistry on section. Often we build some at least schematic cross sections that we're later going to tie to drill hole pierce points. And then the model construction itself. So this is bringing in all the data that is required in order to build the contact surfaces, the structures, the properties that are occupying the 3D model cells. Here's a model. This is sort of a final model of structure and lithological contacts. And then typically we end up with a block model, and that block model is a 3D block model which in the end is going to represent all the exploration criteria. So if we're talking about a couple of dozen exploration criteria, somehow we've got to get each of them represented as a property in each of those 3D grid cells, and that process of getting those in there is going to require geological modeling, geological understanding, working with the geophysical data, working with the geochemical data. From that point, you can move on to the targeting, which is shown schematically here from the same case study. And what's shown here are a series of 6 cross-sectional slices that actually correspond to those same 6 block models that I showed earlier in the presentation. And here we're looking at distance to exhalate contacts, rock code, proximity to a certain class of fault, the northeast faults, looking at a couple of alteration indices, and proximity to borehole anomalies. In a very simple scheme, these could be combined using something called multi-class index overlay, which is suggested here, in which each of those properties is just weighted and scored and then somehow put together into a prospectivity index, which you see in the lower slide, or the lower image. And right away you can see that in that lower image, the cells that are highlighted as the most prospective, you can see them, you can see why they're there by looking at those 6 images, but believe me, in 3D, it's not easy to visualize how these different properties are going to come together into a prospectivity index, especially when you've got a couple of dozen of them. And it's always very illuminating to see how these targets are generated and how, if you interactively change the scores and weights according to opinion or just hypothesis testing, how the targets can shift around. And then the end of the process is drilling new data, validation, and really going around a cycle. And in that cycle, the first steps from objective through conceptual model, exploration criteria, definition, understanding the data requirements, and designing the model, that's fast. You can do that, as I said, typically in a half-day brainstorming session, and then writing it all down might take a day or two, but it's the work of a couple of days with a group of people. And that's really the most critically important step to success in 3D targeting, is getting that plan right. And that's before you head into that data compilation phase, which, as I mentioned, is typically a nightmare. That can go on for months. The model construction itself, that's actually constructing the 3D geological model, bringing the geophysical data, however that's being done, in the geochemical data. That's usually pretty fast. For a typical model, that's sort of 6 or 8 person weeks of time to build a really good model. And then the targeting itself is an interactive process, and that's done sort of in real time, typically with the exploration team. So the thing that we're targeting on is this thing we call the Common Earth model. This is the 3D block model most typically in our representation with all of these properties. Common Earth model is a term from the oil and gas business. It originated with reservoir modeling, in which the geologist, geophysicist, petrophysicist, reservoir engineer had to get all their data into the same space. And the point of a common Earth model, I guess if I can refer to some of the talks that have gone on earlier, is that it's a model that's consistent with everybody's data. It's not a question of right or wrong or true or false. It's almost certainly false. It's almost certainly wrong. But it's the best we can do. And if it's a good model, it's consistent with everybody's data and can be modified, updated as soon as new data comes around. So there you see it through a series of different properties. So that's the goal that we're going to use for the targeting. So the modeling process, just a word on that. There are decisions to be made about scale, about resolution, obviously about the criteria, as I've indicated. But again, the simplest thing to do is put things on a common support in a 3D grid. And just to give you an indication of the sort of process there, we start with geology. Always start with geology. Always start with the structure. The structural model is the most important thing, starting with the biggest, youngest faults and working backwards until you build a fault network that is going to be the structural framework on which you're really hanging the rest of the data. From that comes the formational contacts. If you have the capability of building in a deposit model, you bring it in. We superimpose a grid because we want to model properties in there. And alteration halos, of course, are important. They're often modeled through properties, either lithogeochemical interpolation, geostatistically, or from geophysical inversion, from a combination of the two. But again, at the end of the day, each cell has a number of criteria in it. It knows its story. It may, if in the best case, know something about its certainty or uncertainty. But in any case, everything's on the same quantitative support so that data can be combined for the vectoring. When it comes time to interrogate and vector on that model, you really need a 3D GIS type framework. And these are the kind of questions you want to be able to ask, not only to build that model, but also to query that model. Very simple things that people are used to in 2D GIS. You need to be able to apply them in 3D GIS. That's mechanical, but it's very much a part of the interpretation process. And you need a proper interface to do that. So that's something that we've worked hard on over the years, building what people have come to expect in the 2D GIS world into the 3D modeling world, so these kinds of queries can be made on data. And for the targeting itself, it can be done in many ways. Of course, you can just look visually at a model in which you have all of these different data layers and develop your own targets based on interpretation. But certainly what we've found is when you have a lot of criteria, it becomes very difficult. And you want some kind of computational framework in which you can weight, score, and normalize. These can be data-driven or knowledge-driven. If it's knowledge-driven, that means the individual interpreter is defining the weights and scores and normalizations based on experience. If it's data-driven, it means you have some samples of mineral occurrence within the area, or something, or an area similar enough that you're willing to use the same process, and you train the system. So you use statistics to decide or to define for you what the important criteria are. You learn which criteria are highly dependent on each other. Because statistical dependence or independence comes an important factor when you're computationally combining these things. But in the end, a data-driven framework, if you're able to, if you have the luxury of mineral occurrences on which to train it, is a pretty powerful technique. And again, as I mentioned earlier, that can be weights of evidence, it can be logistic regression, it can be neural networks. In a sense, it doesn't matter. It's a type of computation, but the important thing is that you find a way to statistically understand how the criteria relate to the history of mineral occurrence and then deploy that for future targeting. So that's done in software and in a targeting workflow. So the 3D GIS and the targeting are done together. So again, that's mechanics. The important thing again is the thinking that goes before it. So on to a few case studies. Again, I'm going to go from the regional scale through the prospect scale and the in-mine scale. I'll show two examples at the regional scale, one knowledge-driven, one data-driven, and then the two other case studies are both knowledge-driven, in which the interpreters were supplying the intelligence on how to combine the different parameters. So at the regional scale, this is an example of, it's one example of quite a few now that the GSC have been taking on for regional modeling for targeting. This is their Purcell Basin project. And I'm not going to say a lot about it, but what they're doing is building a very large-scale regional model in which they're trying to combine the map data with whatever down plunge indicators they have from structural mapping, from topography, and from the few drill holes they have, so that they can extend key stratigraphic markers on a regional basis to understand the framework in which future deposits may be found. So those bullet points there are actually from the GSC. This is Eric de Kemp and his colleagues in Ottawa on why they're building those models. So very knowledge driven. I'll turn to another regional study, this one data-driven, in which we're going through the process of formally building that 3D data cube and then using an expert system in order to understand where mineral occurrences may be. This is a good case study because it shows you don't need an extremely data-rich, drill hole-laden project in which you can undertake these kinds of processes. In this case, we have a number of geophysical coverages. We have a geological map. And we've only got a couple of explicitly 2D geophysical methods in which we're explicitly understanding what's going on at depth. So there's a couple of seismic profiles, and there are also a couple of MT surveys. But what can you understand at depth from that kind of coverage? So we start with the geological map. We use structural indicators on surface to help build a small set of schematic sections that are consistent with the map. We use the structural indicators as well as the sections in the map in order to build the basic geological framework. So this is using the implicit modeling framework in GoCAD to initially build the fault network and then to build the contacts within that fault structure. And from that, we build the base 3D block model of the geology. Okay? So you see the block model there is faulted appropriately, and you can see the contacts as well. So just following this diagram around, in the top left was the initial picture I showed of the data. The arrow to the right shows in the center the block geological model. In the upper right, you see a 3D gravity inversion and a 3D magnetic inversion. If you look closely, I realize the images are small, but if you look closely, you definitely see the traces of the fault dislocations and of the formational contacts within the density and susceptibility inversions. So these inversions are done very much geologically constrained. From that, we construct what we call a pseudo-lithology model, which is a geological map that can be compared to the initial geological map, but it's a geological map that's based on geophysical data, because there are many facies within the geological formations that have relatively high or low magnetics or density distributions, and they really represent different units that have importance in the targeting. So all of those different layers are then combined using weights of evidence into a final mineral prospectivity map. And this is done again at a very regional scale. So what you're looking at there in color as a property in the block model is mineral prospectivity, really probability of an IOCG occurrence trained on mineral occurrences that are shown as those little black symbols, little black circles where there are existing mineral occurrences. And from that, you can see there are a number of other interesting prospective areas based on that training and that kind of targeting. Prospect scale targeting, knowledge-driven, Sudbury. The exploration criteria, geometry, trends, lithology, proximity to occurrences, length and grade of anomalous mineralization in drill holes, distance from a major contact, geophysical criteria, and some economic criteria. So initially, a geometric model of the SIC, the Sudbury Igneous Complex, is made. This is the footwall. Then you start building the other criteria into the model. Thickness of the breccia, trends and structures identified from existing mineralization, because we want to follow trends. And there are certainly more criteria in this model than are shown in this picture, but the idea here again is a simple one. It's taking a number of criteria, in this case 6 are shown, and somehow combining them. The multiplication symbol there is really just suggestive. The way of combining these is a little bit more sophisticated than that, but they're being combined into a 3D block model, which will be the prospectivity. So when that's done in 3D, see the property position, individual criteria, distance to the footwall contact, mineralization, proximity to the Sudbury breccia, to trends, distance to drill holes or outcrops showing mineralization, and then again putting it all together. So actually a fairly simple model, in this case built mostly on proximity measures, into an overall prospectivity index where red is high prospectivity. And then they also consider the unknowns. So they look at target potential. In effect, what they do is for each block, they consider what the potential highest score of that block could be if all of the unknowns were positive. And they combine the target potential and the target score in order to rank target. So here again, you can see target potential and target score, shallow and deep. When you're deep, you have a lot more potential, obviously, because there's a lot more unknowns. And then these are combined with basic 3D GIS queries in order to look at a section of the contact and generate targets directly. I promised an in-mine case study, so I'll do this one very quickly. This is actually a very simple example. This was done more than 10 years ago, in fact, at Kidd Creek, where they were looking for targets in the very near mine environment. And again, it was done through a very simple 3D GIS query on a 3D block model that had all of the different exploration criteria in it. So it's more complex than what I'm showing here, but I'll start with showing the rhyolite surface. So the stratigraphy around Kidd Creek is not only vertical, but highly folded, quite complex. The rhyolite surface enveloping the ore body is the prospective surface. These are all the cells in a block model intersected by that rhyolite surface. Again, very simple stuff. Those are the same cells colored by potassium. These are the existing drill holes. Looks like a Swiss cheese, but in fact it's not. These are all the rhyolite blocks greater than 100 meters from the nearest drill hole, shown with potassium. So a lot of prospective ground right around the ore body. There it is with the drill holes off. And there we have it at a certain level of potassium. So again, showing a very simple way of targeting, and in fact this is exactly the process they used to generate some high-value targets in the very near shadow of the ore body. So in summary, what does it take? It takes technology. The technology I don't think is the biggest thing. I think the biggest thing is knowledge and interpretational capacity. You do need to be able to do advanced 3D geological modeling. You do need to be able to construct structural models, lithological models. You do need to be able to handle 3D continuous and categorical property distributions within those models. You need to be able to forward model and invert a range of geophysical methods and be able to invert directly for geological structure. That's key. You need to be able to handle geochemistry within the models. In other words, you need to be able to do the statistics to compute the alteration indices of value and then to geostatistically interpolate those throughout the model space. You need to be able to understand petrophysics. More and more projects that we're working on have petrophysical data, downhole, in situ, wireline data. This is extremely valuable in interpreting the geophysics and geology together. You need to have some kind of 3D GIS query environment, even if it's fairly simple and it's working on simple data structures such as block models. And in the end, you need some way of putting it all together into a knowledge-driven and data-driven target generation, which, as I've shown you, can be deployed across a range of scales from regional through prospect in the mine. Thank you. Yeah, so the question was, once a model is constructed, how do you keep it updated as new data are collected, or perhaps as new interpretational ideas come in? So the updating of a model is either an easy or a hard thing to do depending upon the edit you want to make. Right? So when I talked about the basic order of model construction, starting with the structural model, that basic structural model really controls the fundamental topology of the model, what's connected to what. And the framework defined by that structural model is such that if you're making major changes to the structural interpretation, then you have a lot of remodeling to do. If the structural model is fairly stable throughout the process, then the edits are going to be fairly easy. So in summary, get the structural model right. There's nothing more important than the structural model. It controls everything. Okay, thank you.
All right, for our online participants, that concludes the broadcast portion of this meeting. And we'd like to thank you for your participation today.